The Diels Alder reaction is a famous reaction that involves conjugated dienes reacting with alkenes or alkynes, anything with a pi bond. These are known as the dienophiles. So this term dienophiles means diene loving. Now when these two react with one another, they create products that are known as cycloadducts. And specifically, these cycloadducts are going to create a new six-membered ring. So let's take a look at an example of a Diels Alder reaction. So we have a conjugated diene. We'll go ahead and use 1,3-butadiene. Now all of the electron movement in this reaction is going to involve the pi electrons. So I'm going to go ahead and color code them so we can keep track of what's going on. Now these are going to be reacting with an alkene or alkyne. I'll go ahead and use an alkene that also has pi electrons. Now it really helps in the Diels Alder reaction and related reactions to number your carbons so you can see what is connecting with what. So I'll go ahead and number it like this. Doesn't matter how you number it as long as you keep track of them. Now as far as the mechanism of this reaction, we are going to be starting our arrows at the diene, and you can either start with the blue pi electrons or the green pi electrons. It doesn't matter as long as we have all of the electrons going in the same direction around the circle. So I will start with the blue electrons. The blue electrons are going to go and attack carbon number 6. Okay, so we're going to be forming a bond between carbon 1 and carbon 6. Now at this point, we'll be exceeding the octet rule for carbon number 6. So that's going to push the red pi electrons to move and come over to carbon number 4. And so we're going to be forming a bond between carbon 4 and 5. Now again, that's going to exceed the octet rule for carbon 4, so that's going to push the green pi electrons up in between carbons 2 and 3. And this works well because we've just taken the pi electrons away from carbon number 2, so it's capable of accepting those green pi electrons. Okay. So we have carbons 1, 2, 3, and 4. Our blue pi electrons have just formed a sigma bond between carbon 1 and 6. Our red pi electrons have just formed a sigma bond between carbon 4 and 5. And our green pi electrons have just shifted over to become a double bond between carbon 2 and 3. So we have formed a six-membered ring as a result of this reaction. Now this is a concerted reaction, which means all of this electron movement is happening at the same time. It's also a stereospecific reaction, which we'll see in a second. Now in general, this reaction is not that efficient if you use a simple alkene or alkyne, such as this one here. So of our simplest Diels Alder reaction, this product will form in about a 20% yield. So as we'll see on the next slide, there's a couple of things we can do to the dienophile to improve the yields of the Diels Alder reaction. To improve the yields, the dienophiles can contain electron withdrawing groups. So we'll go ahead and take a look at our simple dienophile here, this alkene. This is our diene. And an example of an electron withdrawing group could be a carbonyl, something that's oxygen containing and capable of resonance with the pi electrons. We'll go ahead and put the carbonyl on both ends of the dienophile. Now what these electron withdrawing groups are doing is they're withdrawing the electrons towards the oxygen atoms. That's going to leave slightly negative charges on the oxygens and slightly positive charges on the carbons that are going to be attacked by our diene. So now it's going to make carbons 5 and 6 much stronger electrophiles so that they can be attacked by the nucleophilic electrons in the diene. So now let's go ahead and show the result of this Diels Alder reaction. We will start with our green pi electrons and show them coming over and attacking carbon number 6. Now at this point we will be exceeding the octet rule for carbon 6, so the red pi electrons will come over and attack carbon number 1. Then, so we don't exceed the octet rule for carbon 1, we're going to push the blue electrons down between carbons 2 and 3, which works because we originally took away the electrons from carbon 3. Now, we have formed a new sigma bond with the green pi electrons between carbons 4 and 6. And we've also formed a new sigma bond with the red pi electrons between carbons 1 and 5. Now our blue pi electrons are going to be between carbons 2 and 3. These pi electrons are often the biggest mistakes that students make, so they usually forget to draw these pi electrons. So always make sure you keep track of all of the pi electrons that moved throughout the mechanism. Now, as far as our electron withdrawing groups, they're going to still be on carbons 5 and 6. Now, carbon 5 and 6 are sp3 hybridized now. Originally, they were sp2. So we do have a tetrahedral shape around them. Now, we will talk about the stereochemistry in just a little bit, but I'm going to go ahead and indicate the stereochemistry of these electron withdrawing groups by drawing them as both wedges. And as we'll see in a little bit, Diels Alder maintains the stereochemistry of the dienophile. So since our dienophile starts out as a cis alkene, we're going to end up with a cis ring, where both of those electron withdrawing groups are on the same side of the ring. Now, because we have the electron withdrawing groups on the dienophile, we will end up with much higher yields than 20%. Okay, another example of a great electron withdrawing group are cyano groups. So if you see CN attached to the alkene, that's the same as a C triple bonded to an N. So a cyano group, as well as any sort of carbonyl, a C double bond O, are very common electron withdrawing groups. Now there's a few properties of the Diels Alder reaction that we need to know about. First, the diene must be in the S-cis conformation. So I've drawn 1,3-butadiene in both conformations. We have the S-cis here and the S-trans over here. Now with 1,3-butadiene, we can rotate around this single bond to go back and forth between the cis and trans conformation. But it must be in the cis conformation for the Diels Alder to occur. So once it does reach that S-cis conformation, we can have the Diels Alder reaction proceed. When it is in the S-trans conformation, this reaction will not work. As you can see, we could have the attack of one of the alkenes, but now in order to have the pi electrons come all the way over, it's just too far away. It doesn't line up very well for this reaction to proceed. So this will not occur. It must be in that S-cis conformation. So for certain molecules that are locked in an S-trans conformation, such as this one here, we can see that we have the single bond separating our conjugated double bond. And if we were to draw a line down the single bond, we have both of the double bonds on opposite sides. So currently this molecule is in the S-trans conformation. Now we cannot rotate around this bond because it's in a ring, so it's locked in this particular conformation. So this is an example where we cannot have Diels Alder occur. If we have our diene, our conjugated diene, not in a ring, we do have the rotation around that single bond to allow it to adopt the S-cis conformation. Now, as far as stereochemistry of the Diels Alder reaction, the main thing we need to focus on is the stereochemistry of the dienophile. We have to make sure it's retained as we go from the reactants to the products. In our first example, our dienophile, which contains our two cyano groups, is currently in the cis conformation. So that means we need to make sure our product also has those two groups cis to one another. So we'll go ahead, I'll show the mechanism for forming our product. So we make a 6-membered ring. Now I'm going to show our cyano groups as either both wedges, which would make them cis, or I can draw them as both dashes. These are meso compounds, so either way we draw them would make them the same. Now with our second example, our dienophile is in the trans conformation. So our diene will react. We will form our 6-membered ring. Then we need to indicate the two CN groups as trans by making one a wedge and one a dash. Now you should recognize that this is a chiral molecule. There is no plane of symmetry. So that means we would also form this molecule's enantiomer. So we can either show that by putting plus En for plus enantiomer, or you can show plus the actual enantiomer in which the top cyano group is a dash and the bottom is a wedge. So either way would indicate the fact that we have a racemic mixture as a result of this reaction. The endo rule in the Diels Alder reaction must be considered when the diene is a ring and the dienophile contains electron withdrawing groups. And the reason that we have to consider the endo rule is because the product formed will be bridged. Now the endo rule says that the electron withdrawing groups will be opposite or anti to the smallest bridge. So to illustrate the endo rule, let's go ahead and draw the product of this Diels Alder reaction. So we have a conjugated diene, which is enclosed in a ring. We're reacting it with a dienophile that contains an electron withdrawing group. So again, it's very important to number your carbons to keep track of everything. So I will just go ahead and number them like this, and it doesn't really matter how you number them. Now, this really isn't any different from the Diels Alder reactions we saw previously. So first, the conjugated diene is going to attack the dienophile. So I will show the electrons between carbons 4 and 5 coming over and attacking carbon 6. Now that's going to cause the pi electrons between carbon 6 and 7 to come over and attack carbon 2. Then that's going to shift over the electrons between carbons 2 and 3 to between 3 and 4. Now we need to keep track of what is connected to what. Now we are forming a 6-membered ring because this is a Diels Alder reaction. So I'll start by drawing the 6-membered ring. Now the ring is being formed between carbon 5 and 6, 7 and 2, and carbons 3 and 4 are also connected to carbons 2 and 5. Now we know that we have a double bond between carbons 3 and 4. We also have carbon 1. Carbon 1 has not gone anywhere. Carbon 1 is still connected to carbon 5 and carbon 2. So I'm going to draw it like a little bridge here. And that is our carbon 1. Now carbon 1, we can imagine, is sticking up above the plane of the ring. So I will go ahead and draw it as kind of wedges to give it 3 dimensions. So So we'll show it forming a bridge above our ring. Now for our electron withdrawing group, which is this group here, we now have an sp3 hybridized carbon number 7, so we need to show the stereochemistry of this electron withdrawing group. Now our bridge is carbon number 1, and our bridge is coming up above the plane of the ring. That means our electron withdrawing group, which needs to be opposite the smallest bridge, is going to be a dash, going below the plane of the ring. Now I can redraw this in a different way to give it more of 3 dimensions. So you can imagine this 6-membered ring is kind of like a piece of paper that is folded in half. We have carbon 6, 5, 4, 3, 2, and 7. Now we have our double bond here. And then carbon 1 is going to be a bridge that's coming up above the molecule. And our electron withdrawing group, which is our ketone, is coming down. So this ketone is currently in what's known as the endo position. Now the other group on carbon 7 is a hydrogen, and we can draw the hydrogen going in the opposite direction, and this is known as the exo position, meaning it's on the same side of the ring as the smallest bridge, which is carbon number 1. Now the endo position is preferred when there is a choice for where the electron withdrawing groups are going to go. But remember, with the Diels Alder reaction, we do have to maintain the stereochemistry of the diene. So we're going to look at 2 more examples of forming bridged products. In our first example, our electron withdrawing groups are cis to one another. In our second, they are trans. So we need to maintain that stereochemistry when we draw our products. So again, I will number the carbons. Then we'll go ahead and draw our arrows. We'll start them over here. We'll have carbon 5 form a bond with carbon 6. Carbon 6 is going to come over and form a bond, carbon 7 is going to come over and form a bond with carbon 2. We'll shift these down here between carbon 3 and 4. So again, we are forming a 6-membered ring. Now our double bond is going between carbons 3 and 4, and we have carbon 2 and 5 still connected to carbon 1. So that is going to be our bridge. And again, I'll just show these as wedges so we can give 3 dimensions to the molecule. So our bridge is coming up. Now we have our electron withdrawing groups on carbon 6 and 7. Those carbons are now sp3 hybridized, so we do need to show stereochemistry. Since they started off as cis, they are also going to be cis in our product. And since our bridge is pointing up and we want to follow the endo rule, we're going to have both of our cyano groups as dashes. And that would be our product. I'll go ahead and redraw it in the other form. Okay, so we're going to have the cyano groups pointing down in the opposite direction as our smallest bridge. Okay, so you can draw your products in either form, whichever is easiest for you to see and draw. Okay, let's go ahead and take a look at this next one. So it's really going to be the same sort of mechanism, same type of product. We're just going to need to change the stereochemistry of our electron withdrawing groups. So we have our concerted reaction forming our six-membered ring. I'm keeping the numbering the same. We have our bridge with carbon number 1. So I'll go ahead and draw it as wedges. Okay, now since our diene started as trans, we need to have the trans stereochemistry. So one of our cyano groups is going to be a wedge and one will be a dash. It doesn't matter which one you choose. Now you should recognize that this product is an achiral molecule, so you would also get its enantiomer. We'll go ahead and redraw it in the other way. Now our cyano group that is a wedge will be in the exo position. The one that is a dash will be in the endo position. So with the trans alkenes, we really can only get one of those electron withdrawing groups following the endo rule. But since we have to maintain that stereochemistry, one of the groups will have to be in the exo position. Let's go ahead and do a couple of practice problems, and then we'll take a look at the applications of the Diels Alder reaction. So starting off with problem number 1, we have our conjugated diene, and we have our dienophile, the alkene. Now, taking a look at this conjugated diene, it's currently drawn in the S-trans conformation. However, it's important to note that we can rotate around this bond in order to get the S-cis conformation. So even though it's drawn this way, it can still adopt the S-cis conformation. Now, it needs to be in the S-cis conformation in order for the reaction to proceed. So we'll go ahead, number our carbons so we can keep track of everything. Then we'll go ahead and draw our concerted mechanism. We will be forming a six-membered ring. Our bonds will form between carbons 6 and 1 and 5 and 4. And since our dienophile is in the cis conformation, we need to have the cis configuration for our electron withdrawing groups in our product as well. So I'll go ahead and draw these both as wedges. And this is a meso compound. It does have a plane of symmetry straight down the middle, so we don't need to worry about any enantiomers. Okay, so for our second problem, we have a conjugated diene in a six-membered ring now. So again, very important to number our carbons. Okay, so now for our mechanism. I'll go ahead and start with the electrons between carbons 1 and 2. They are going to come over, and we are going to form a bond between carbon 1 and 8. Those pi electrons are going to come over and form a bond between carbons 7 and 4. And we'll push those pi electrons up between carbons 2 and 3. So again, we will be forming our six-membered ring. And the ring will form between carbons 1, 2, 3, and 4, and 7, and 8. Now our double bond is here between carbon 2 and 3, and we still have carbon 1 attached to carbon 6 and carbon 4 attached to carbon 5, so we don't want to leave those out. It gets a little tricky fitting all these carbons in here, but they are still there. They haven't disappeared. Now I'll give this 3 dimensions by drawing wedges. So we have a 2-carbon bridge here. So now for our electron withdrawing groups, we started out in the trans configuration. So we will have one of the groups be in the endo position and one be in the exo position. Doesn't matter which one you choose. I'll go ahead and put the bottom one in the endo position and the top one in the exo position. This is a chiral molecule, so we would get its enantiomer as well. As we've seen throughout this video, the Diels Alder reaction is very good at making six-membered rings. So this type of reaction is very useful in synthetic chemistry, and it can be used to make any sort of drug or natural product that contains a six-membered ring. So for example, steroids. Steroids actually have several six-membered rings. This is the basic backbone of a steroid molecule. So we have 1, 2, 3 fused six-membered rings, as well as a five-membered ring. This molecule as a whole is an example of cortisone. Now, a way to make cortisone is using the Diels Alder reaction. So this can be one of the starting molecules, and this is going to act as our dienophile. So you can see we have carbonyls here, so those act as the electron withdrawing groups to increase the yield of this reaction. Then we have our conjugated diene, the 1,3-butadiene. So once these guys react, we form a new six-membered ring, and now we have taken the first six-membered ring and fused it with the second one. So this reaction continues in many, many steps. There's several other types of reactions involved as well, but ultimately we can form the structure of cortisone. Now, the Diels Alder reaction is also used to make Taxol. This is an example of the drug Taxol, which is used in cancer treatment, as well as for tetracycline, which is a common antibiotic. So you can see here we have 1, 2, 3, 4 fused six-membered rings. So in the formation or synthesis of this particular drug, the Diels Alder reaction is also useful.